Okay, we're on our course page here in MyMathLab, and I'm going to work through some homework problems. And so let's go to the Assignments tab and click on Homework 1, Module 1. And we'll go through a few of these questions. So first one, number 1, find the following limit or state that it does not exist. So we have the limit as x approaches 2 of x squared minus x minus 2 over x minus 2. Now this is just a rational function, right? A polynomial divided by a polynomial. So we can just plug in the number as long as we're not getting 0 in the denominator, but we are getting 0 down here. So notice when we plug in 2 here, we get 0. If we plug in 2 in the numerator, we also get 0, right? 4 minus 2 minus 2. So we end up getting 0 over 0. Now, you might be tempted to say, oh, this means that the limit does not exist, but that's not correct. The limit does exist. In fact, remember that the limit doesn't have anything to do with what you get when you plug in 2, but what do you get when you plug in values that are close to 2, like 1.999 or 2.001? So how do we compute this limit? Well, let's actually do this here. What's the limit as x approaches 2 of this? And remember, what we need to do is to factor. So let's write equals limit as x approaches 2 of. Now, how does the numerator factor? Well, the fact that when we plug in 2, we get an output of 0 means that x minus 2 is going to be one of the factors. In fact, you can see that x minus 2 times x plus 1 is how this factors, right? FOIL that out, you'll see that's what you get. So what we can do is cancel this factor here, and we get that this is equal to the limit as x approaches 2 of x plus 1. Okay, and now we can just plug in 2. We just have a polynomial here. We can just plug in the value, and we get 2 plus 1, which is 3. Okay, so that's our answer. So again, when we plug in 2, we get 0 over 0, which is undefined. But the limit doesn't have to do with what you get when you plug in the number, but what do you get when you plug in numbers close to 2 but not equal to 2? So how do we figure that out? Well, we do what we just did. So if we go here, we type in 3, check our answer, and notice it says correct. By the way, we can also go to Desmos here. Notice that f of x is this function right here. That's the function we had. We could say, what is f of 2? And let me type it in. Notice it says it's undefined. But what if I were to plug in a different number besides 2, like 1.9 or 1.999? Notice my outputs are really close to 3. Or what if I plugged in 2.0001? Notice my output, again, is really close to 3. In fact, here's a graph of the function right there. If you plug in 2 itself, it's actually undefined. But notice that plugging in numbers close to 2, those inputs that are close to 2, like 1.96, we get an output that's close to 3, right? These outputs are close to 3 here. So again, Desmos doesn't actually show the open circle there unless you click on it. But you can see from the graph here also that the limit as x approaches 2 of the function is 3. Okay, let's skip on down to question number 4. The limit as x approaches 14 of this. And again, if you plug in 14, you're going to get 0 over 0. 14 squared actually is 196. So you get 0 over 0. So we're going to do the same thing for this one. We have the limit as x approaches 14 of x minus 14 over x squared minus 96. Now notice that the denominator is a difference of squares. So the way that it's going to factor is x plus 14 times x minus 14. And again, 14 times 14 is 196. So this time we have these x minus 14 factors that will cancel. And we have limit as x approaches 14 of, well, notice that we have just 1 left in the numerator, and we have x plus 14 in the denominator. So now we can just plug in our 14. And when we plug in 14, we get 1 over 14 plus 14, 1 over 28. Okay, so that's our final answer. So here we'll click 1 over 28. Check answer, and we got it correct. Okay, now move on to number 5. How do we do this one? Well, it's basically the same thing, right? We're going to factor the numerator. So we have x minus 4 in the denominator, and we're going to have to factor the numerator. In fact, when we plug in 4, notice you get 16 plus 24, which is 40, minus 40, which is 0. And you plug in 4 in the denominator, you also get 0. So the way that this factors in the numerator, well, one hint, it might be a little tricky to factor this because you might think, well, there's a bunch of ways you can multiply numbers to get 40, like 1 times 40 or 2 times 20. 4 times 10, 5 times 8. But actually, we have a little bit of a hint. The fact that when we plugged in 4, we got 0 in the numerator means that x minus 4 is going to be one of the factors. In fact, what's the other factor going to be? It will be x plus 10. If you FOIL this out, you see x times x is x squared. You get a plus 10x from these outside two terms and minus 4x from the inside two terms. So that gives us a plus 6x. And minus 4 times 10 is negative 40. So again, we cancel these factors. And what we get is the limit as x approaches 4 of x plus 10. But we can just plug in 4 now, and we get 4 plus 10. So I don't have to keep writing the limit symbol anymore because now I'm taking the limit. You should write a limit right here and right here, but we don't need to write the limit symbol down here because we're actually taking the limit. So going back to MyMathLab, again, your answer would not be does not exist. The answer is 14. So let's check our answer, and there we go. Okay, moving on to number 7. How would we do this one? Well, again, you're going to factor both the numerator and the denominator this time because it turns out that when you plug in 7, you can check you're going to get 0 over 0. The denominator is going to factor to be x plus 7 times x minus 7. I think the numerator will factor to be x plus 10 times x minus 7. And you're going to cancel the x minus 7 factors and then plug in the 7 and you'll get the answer. So I'll let you do that one. Okay, what about number 8 here? By the way, the numbering of the problems might be different when you're actually doing these because I might change up these from semester to semester here. But what's the limit as x approaches 3 of 4x? Well, notice this is just a polynomial. We can just plug in the 3 and it'll give us the correct answer. Okay, so what do we get? Well, it's going to be 12. 4 times 3 is 12. Let's check answer. We got it. Okay, same thing with number 9 here. You can just plug in the number. It should give you the correct answer. Okay, now the next one, we're going to have to factor things. So the numerator is going to be a difference of squares, x plus 9 times x minus 9. You cancel the common factors, and then you just plug in the 9 at the end. Okay, now this one here is actually number 11. This gives us a function f of x equals this rational function here, right? It's a polynomial divided by a polynomial, but there's 3 parts. There's a, b, and c. So what's the limit as x approaches 8 of this function? Well, you're going to do that just like the previous ones that we did. You're going to factor this. So you can rewrite it as limit as x approaches 8 of this. Then factor this. You should get x minus 8 being a factor in both the numerator and denominator, and you can cancel those. That's how you can figure out part A. Actually, parts B and C are easier because when you plug in 0 and when you plug in negative 6, you're not going to get 0 down here. So you just plug in those numbers. That'll give you the correct answer. So once you do A here, B will open up, and then once you do B, C will open up. By the way, one thing I should mention, if you go to the bottom, there's some helps here, one called Help Me Solve This. Now, if you click Help Me Solve This, it's gonna walk you way through doing the problem, but it's gonna mark it incorrect. And so you walk your way through doing the problem. It'll be incorrect, but then you can redo the problem just with new numbers. Now, if instead of doing Help Me Solve This, if you just do View an Example, it'll do a worked out example for you that's not exactly the same as the example that we're working on. But it won't mark your problem incorrect when you do that. So just do View an Example. It's probably easier. By the way, there's Get More Help. You could also do Ask My Instructor. Now, the video, that's not my videos that I've made, but there might be a different video that MyMathLab has created. Okay, now moving on here, we have a table of values, and we're asked to estimate what's the limit as x approaches 6 of this function. So here's our inputs, our x's, here's our outputs, the f of x's. So notice, for example, that f of 6.01 would be 9.01. Okay, f of 6.001 is 9.001. Now notice we're not told what f of 6 is, but again, the limit doesn't have anything to do with what you get when you plug in 6, only what you get when you plug in values that are close to 6. And notice when we plug in these values that are getting close to 6, our outputs look like they're getting close to 9. So our answer here is just going to be 9. So type 9, check answer. We got it correct. Okay, now what about number 17? This one's very similar, but notice f of 6 is 17. So does that mean that the limit here is going to be 17? No. Right? Remember, the limit has nothing to do with how the function is defined at that number, at the 6 in this case. In fact, f of 6 is 17, but the limit as x approaches 6 is still going to be 9 here. right? These, when you take inputs that get close to 6 but not equal to 6, the outputs are close to 9. And the closer those inputs are to 6, the closer our outputs are going to be to 9. So again, this one would also be 9. Okay, now what about this one here? Notice it's asking us about left and right hand limits. Use the table of values to estimate the left and right hand limits, as well as the ordinary two-sided limit. So notice it's not telling us what we get when we plug in 6, but that doesn't matter. Notice if we plug in numbers a little less than 6, we're getting outputs that are close to 9. But when we plug in numbers a little bigger than 6, we're getting outputs that are close to 2. So as we approach 6 from the left, our limit is going to be 9. So the limit as x approaches 6 from the left. So that's negative doesn't mean negative 6. It means positive 6. We're approaching positive 6, but from the left. Okay, so that answer is going to be 9. Okay, now when we approach from the right, what's the limit as x approaches 6 from the right? Well, our outputs are going to be getting close to 2. Now, what about the ordinary two-sided limit here? The limit as x approaches 6. Well, the fact that the left and right-hand limits do not agree, the left-hand limit is 9, the right-hand limit is 2, means that this two-sided limit is going to be does not exist. Okay, so let's click check our answer, and we got it correct. All right, now what about this one? We have the limit as x approaches 4 from the left of some function is 9. Now, we're not given a formula for the function. We're just told that the limit as x approaches 4 from the left of that function is 9. But the limit as we approach 4 from the right is 2. Okay, then what about the ordinary limit, the two-sided limit? Well, again, the fact those numbers do not agree means that this limit does not exist. If they had both been 9, well, then the answer would be 9. Or if they had both been 2, the answer would be 2. But if they disagree, then the limit does not exist. Okay, for this next one here, we have a graph. Let me scoot this over so we can see the graph a little bit better. Use the graph of this function h in the given figure to find the values or state that they do not exist. So what is h of 4? Well, notice it's a little tricky to see the graph. By the way, you can get it to pop out by pressing this bottom button. It pops out. I don't always necessarily like the way the graph looks when you do the pop out one. So you can maybe do the zoom in button. So let's zoom in a couple times. And by the way, you can move this up and down right here to kind of see things a little bit better. So the question is, what is h of 4? Well, if we go over to 4, what is h of 4? Well, is it this value 6 here? No, it's the value 8. h of 4 is going to be 8. So let's go and plug it in. H of 4, check our answer, is 8. Okay, now part B, what's the limit as h approaches 4 of this function? Well, notice if we put inputs that are really close to 4, like 3.9 or 4.1, we're going to get outputs that are close to 6. So even though h of 4 is 8, the limit as x approaches 4 of h of x is going to be 6, this value right here. Let's type 6. Because again, the limit has to do with what you get when you plug in numbers close to the number. Now, what about h of 7? Well, h of 7 here, I don't see a dot at all. It looks like h of 7 is undefined. And by the way, we don't say h of 7 doesn't exist. When we're talking about a function value, we say undefined. For a limit, we say does not exist. But h of 7 is undefined. Okay, now what about the limit as h approaches 7? Well, notice if we plug in numbers that are really close to 7 but not equal to 7, we're getting outputs that are really close to 3. So for example, if I plugged in 6.9, looks like my output would be something a little bigger than 3, like 3.1. Or if I were to plug in 7.0001, looks like my output would be like 3.00 something. Okay, so my outputs are getting close to 3. And that's the correct answer. Okay, now last of all, what is the limit as x approaches 8? Well, actually, nothing really interesting is happening at 8. In fact, notice h of 8 is just 4. It's over here at a height of 4. And that's also what the limit will be, the limit as x approaches 8. So not only when we plug in 8 do we get an output of 4, if we plug in numbers that are close to 8, we're also going to get outputs that are close to 4. So in this case, the function is what's called continuous. We'll talk about continuity later. So the function value and the limit actually are the same. So h of 8 is 4, but also the limit as x approaches 8 of h of x will also be 4. Okay, now this one is asking us about a left-hand limit. Use the graph of f shown to the right to find the limit. If necessary, state that the limit does not exist. So this says, what's the limit as x approaches 1 from the left? Again, this is not -1. This is actually +1, what we're approaching from the left. So if we were to go here on the graph and look at where 1 is, so notice if we f of 1 is going to be up here at 3, but also if we're approaching from the left, if we plug in numbers a little bit less than 1, we're going to get outputs a little bit less than 3, but they're getting closer and closer to 3 when we plug in these inputs. So the limit as x approaches 1 from the left will be 3. Now, if we approach from the right, if we took values approaching from the right, our outputs would approach 1. So if this were a little plus up here, our answer would be 1. But let's check our answer. Okay, now let's do the next one. Use the graph of the function g to find the limit. So we're being asked for what's the limit as x approaches -1 from the left and also -1 from the right. So if we go on our graph, here is the y-axis here. Here's 0. So -1 is right here. As we approach -1 from the left, if we take numbers a little to the left of -1, like -1.001, our outputs are going to be approaching 2 up here. But if we approach from the right, if we take inputs that are approaching -1 from the right, our outputs are going to be approaching 0, right? So we approach 2 from the left, we approach 0 from the right. So the left-hand limit is going to be 2. The right-hand limit is going to be 0. And what about just the ordinary limit then? Well, again, the fact that these two limits do not agree, the left and right-hand limits do not agree, this one is going to be does not exist. Let's check our answer. And we got it correct. All right, now what about this one? We're trying to find what's the limit as x approaches -1 of the function, and also what's the limit as x approaches +1 of the function. So here's -1 and there's +1s, right? Something interesting is happening here at -1. Something interesting is happening here at +1, right? So here's our x-axis here. There's -1, there's 1. So what's the limit as x approaches -1 from the left? Well, as we approach -1 from the left, our outputs are approaching 1, it looks like. When we approach -1 from the right, our outputs are also approaching 1. So this should be 1. So this should be 1 and 1. Check answer. And so the ordinary limit as we approach -1 should also be 1, since both of those agree. So notice we have a limit of 1 right here as we approach -1. That height there of that hole there is 1. Okay, now what about when we approach +1 from the left or +1 from the right? Well, notice when we approach 1 from the left, we're way up here at 4. When we approach -1 from the right, we're down here at -1. So we have 4 and -1. And so again, down here, this one is going to be does not exist because the left and right hand limits do not agree. This will be does not exist. Okay, moving on. Use the graph of g shown to the right to find the limit. When necessary, state that the limit does not exist. Okay, what's the limit as x approaches 3 of g of x? So we go here. Okay, so I've made it so you can see it a little bit better. What's the limit as x approaches 3? Well, notice when we approach from the left, our outputs are getting close to 4. When we approach from the right, our outputs are getting close to -2. So the left-hand limit is going to be 4. The right-hand limit is going to be -2. So what can we say about the limit? Well, the limit does not exist. Okay. Now, by the way, what is g of 3? G of 3 would be 1. Okay, g of 3 would be 1. But remember, again, the limit doesn't have anything to do with how the function is defined at 3. Right? G of 3 is 1. But as we approach 3, so as we're approaching 3 from the left, our outputs are approaching 4. As we approach 3 from the right, our outputs are approaching -2. So the left and right hand limits do not agree. The left hand limit would be 4. The right hand limit would be -2. So the limit does not exist. Okay, now this one is a bunch of true false questions. So which of the statements A through K about the function y equals f of x graphed here are true and which are false? So we have this function. The statement f of 0 equals -1 is what? Well, notice here, here's the x-axis here, and here is 0. Well, f of 0 is actually 0. Okay, so f of 0 is not -1. That's false. Now, part B, f of 0 equals 0, that is true. Okay, so right, so we're asking what's happening at 0. Let me make this a little bigger here. What's happening at 0? Well, what about at 1? Notice f of 1 equals 0. Well, is f of 1 0? No. If this were filled in circle right here, f of 1 would be 0. But notice f of 1 is down here at -2. So f of 1 equals 0, that's false. But f of 1 equals -2, that's true. Okay, now what about the limits? Does the statement limit as x approaches 0 equals f of x exists is it true or false? What about the limit as x approaches 0? Well, notice if we take values that are close to 0, like negative 0.0001 or positive 0.00001, our outputs are going to be really, really close to -1. So as we get close to 2, as we get close to 0, but not equal to 0, our outputs are getting close to -1. So the limit's going to exist. The limit's going to be -1. Even though f of 0 is 0, the limit as we approach 0 is going to be -1. So the limit exists. That's true. And the statement limit as x approaches 0 of f of x is -1. That's also true, right? We are approaching -1, right, as we go from the left and the right. Now, the statement limit as x approaches 0 of f of x equals 0, that's false. F of 0 is 0. But the limit as x approaches 0 of f of x is not 0. It's actually down here at -1. Okay, what about limit as x approaches 1 of f of x? What is that? Well, notice as we approach 1 from the left, our limit will be 0. We're having a left-hand limit of 0, but we're having a right-hand limit of -2. Okay, so the left and right-hand limits do not agree. So the limit is 0, that's false. The limit is -2, that's false, because the limit does not exist, right? The statement the limit does not exist, that's true. Okay, the limit does not exist. Okay, we could talk about the left-hand limit, which would be 0, or the right-hand limit, which would be -2. But the ordinary limit, the two-sided limit, does not exist. Okay, so that's true. Okay, now what about this one here? We have the limit as x approaches -3 of this. Well, notice we might just think, oh, let's just go ahead and start factoring things. But actually, notice when we plug in -3, we don't get 0 in the denominator. So actually, this one's really easy. We just plug in -3 everywhere we see an x, and that will give us the correct answer. Okay, if you have a rational function, right, like a polynomial divided by a polynomial, you can always just plug in the number unless you're dividing by 0 down here. Now, we are going to be dividing by 0 lots and lots and lots of times. In fact, maybe most times. But anytime you're not dividing by 0, you can just plug in that value and it should give you the correct limit, okay, when you have a rational function. So for this particular one, how would you write it? Well, limit as x approaches 3 of this, we can write equals. And notice I got rid of the limit symbol. I'm not writing limit as x approaches -3 anymore. I can just say equals this, and I'm just plugging in -3 everywhere we see an x. Now, the key thing here, you have to keep track of the negatives. So -3 squared is going to be +9. So 3 times -3 squared, that's going to be +27. And then -15 plus 7. In the denominator, you have -12 minus 7. So what you end up getting is 19 over -19. Now, if you plug in 19 over -19, it might mark it wrong because it says simplify your answer, because this simplifies to be -1. So you always have to be careful to read what's in the blue here. Simplify your answer. So this should be -1. Okay, now for this one, though, notice we are going to get 0 down in the denominator. Now, what do we get in the numerator? Well, if we plug in -3, we're going to get 9 minus 39, which would be -30, plus 30, which is 0. So in this case, you're just going to factor. You're going to have an x plus 3 factor. I think it'll be x plus 3 times x plus 10. You cancel the x plus 3 factors, and you're just going to get limit as x approaches -3 of, and it's just going to end up being x plus 10. And if you plug in -3 into x plus 10, you get -3 plus 10, which is 7. So I think this is 7. So I did that in my head, but you might want to write that out. Okay, now what about this one? This one is quite a bit different than the previous ones. If we plug in 3 here, we do get 0 in the denominator. We get 9 plus 6 minus 15. That's 0. But we don't get 0 in the numerator. So if you ever have a rational function, right, like a polynomial divided by a polynomial, and when you plug in the number, you get 0 down here, but you don't get 0 up here, what that means is essentially you have a vertical asymptote at that 3. So it's going to mean the limit does not exist. Okay, if you have a 0 over a 0, it could exist. In fact, lots of times it does exist. But if you have something other than 0, so in this case, we'd have 7. When we plug in 3 here, 7 over 0, that's going to mean the limit does not exist because there's going to be some type of vertical asymptote. We'll talk more about this in the next module, module 2. Okay, and the last problem we'll look at, use the properties of limits to find the indicated limit. It may be necessary to rewrite the expression before limit properties can be applied. What's the limit as x approaches 36 of this? Now, this is not a rational function because it's not a polynomial up here over a polynomial, but it's going to act very similar to a rational function. In fact, if we just plugged in 36, notice we're going to get 0 over 0, right? The square root of 36 is 6, right? 6 minus 6 is 0, over 36 minus 6, which is 0. But notice, though, we can't really factor things. I mean, I guess you could factor the denominator if you're really clever, if you use square roots. So how do we do this, though? How could I find this limit? Again, when we plug in the 36, we get 0 over 0, which is an indeterminate form. 0 over 0 is undefined, but that doesn't mean the limit does not exist. In fact, the limit is going to exist. And what we're going to do is we're going to multiply the numerator and the denominator by the conjugate of this. So the square root of x minus 6, the conjugate is going to be the square root of x plus 6. And we're going to multiply both the numerator and the denominator by that. Okay, and the reason that we multiply by a conjugate is so that things will simplify nicely. In fact, let's leave the denominator not multiplied out. Let's leave it like this. But when you multiply something by its conjugate, it's going to simplify nicely. In fact, we have the square root of x times the square root of x, right? If we FOIL this out, this times this, we FOIL this out, the square root of x times the square root of x is just x. But then we're going to have a plus 6 times the square root of x and a minus 6 times the square root of x. And those are going to cancel. And last of all, we'll have minus 6 times plus 6, which is minus 36. So notice what we get in the numerator is just x minus 36. And that's exactly one of the factors in the denominator. Okay, fortunately, we didn't multiply out that denominator, right? Because then this would be a big mess down here. But we can now cancel these. And notice what we get is the limit as x approaches 36 of 1 over the square root of x plus 6. And now when we plug in 36, we're not going to get 0 down here. In fact, we'll get 6 plus 6. So what you end up getting is 1 over, and by the way, I'm not writing the limit symbol anymore because we're actually taking the limit now. We're plugging in the 36 here, and we're not going to get a 0 in the denominator when we plug it in. So what we end up getting is 1 over 6 plus 6, which is 1/12. Okay, 1/12. By the way, you could go into Desmos or a calculator and figure this out kind of ahead of time. You could take a look at this limit and try to plug in a number that's really close to 6. So maybe plug in like 36.001. Plug that in for x there and there. Make sure you plug in the same value for x there and there, a value that's really close to 6, or really close to 36, I should say. And your output should be some kind of crazy decimal, but actually the crazy decimal that it's close to will be the decimal for 1/12. Okay, so our answer here is 1/12. In fact, here in Desmos, I defined the function f of x to be what it was. We could say, what is f of 36? And notice it's going to be undefined, but that doesn't mean the limit does not exist. What we need to do is plug in a number close to 36, like 36.0001. Or maybe add a couple more zeros, right? We're getting a crazy decimal here, but what is that crazy decimal? By the way, we should also plug in something a little less than 36, like 35.99999. And notice, again, our outputs look like they're getting closer and closer to this number, 0.08333333. So what is that number? Well, it turns out, notice 1/12, that's that. Okay, so when we plug in 36, it's undefined, but when we're plugging in numbers close to 36, we're getting outputs that are close to this crazy decimal, which is really 1/12.